Hello, algebra students. Today we are going to be talking about modeling exponential growth and decay, continuing on with these exponential functions that we've been learning about. So first we need to kind of discuss the difference between exponential growth and exponential decay, and as you can probably guess, growth is going to mean an increase of some kind, and decay will mean a decrease of some kind. So let's see how that looks when we graph it. So we're on page 617 in the textbook, and it says when you graph a function f of x in a coordinate plane, the x-axis represents the independent variable, that's what we've seen all year, and the y-axis represents the dependent variable, that's our y. Therefore, the graph of f of x is the same as the graph of the equation y equals f of x. They're just here telling you that y is equal to f of x, which we've already seen again. That's just function notation. So they're telling you that because when we use our calculator today to see the graphs of exponential growth and decay, instead of entering f of x somewhere, you're going to have to use the y equals screen because they're the same thing. So you'll use that form when we plug in the calculator. So they're asking us to use the calculator to graph this function right here. This f of x is equal to 200 times 1.10 to the power of x. So we're going to go to y equals. If you have anything in there, go ahead and clear it out. And we'll type in, just as it's written here, 200 times 1.10 to the power of x. So we're going to have to use our caret here. And then it moves us up into an exponent, and then we can use the x button to put in power of x. And then it says to change our viewing window. This is going to be really important with exponential functions so that you can see the whole graph. So instead of going to the graph first, I'm going to go ahead and go to Window, and I'm going to change it based on the parameters that they give me here. So it says that they want my x minimum to be negative 20, so I'll type in negative 20 for x min, and then to positive 20. So our x values are going to go from negative 20 to positive 20, and they want us to use a scale of 2. And then for y, we're going to do a minimum of negative 100 up to a maximum of 1,000 with a scale of 50. And now it asks us to copy onto our textbook page the curve that we see. So let's go ahead and go to graph. And here we see the exponential function graphed on our calculator. And we can sketch that over here. And now it asks us to describe the end behavior of the function. What is happening as x is increasing without bound? Like x is not being stopped. That's why we have an arrow down here. And so what is happening? Describe the end behavior as x increases without bound. So as x increases, what's happening to y? Well, y is approaching infinity. It's just going to get higher and higher and higher and higher. Next, it asks us to use the trace feature and move the cursor to the left along the curve. So I'll hit trace, and then I'm going to move my arrow left. And what do you see happening to the end behavior as x decreases? Well, the values are getting smaller and smaller and smaller and smaller. And we've talked about in class, will these values ever get to 0? No, they won't, because we're essentially using those geometric sequences again. We're like dividing, as we're moving to the left here, we're getting smaller and smaller and smaller. Smaller parts of an actual integer are never going to get to 0. So as long as we're dividing by something that's not 0, we'll never get to 0. So as x is moving to the left, as x is decreasing without bound, infinitely decreasing, y is approaching 0. Now technically, if we're describing this behavior, we should say as x increases without bound, y approaches infinity. As x decreases without bound, y approaches 0. All right, pretty basic stuff. So now we're going to move on to the reflect questions. And it asks us to describe the domain and range of the function using inequalities. This is a throwback to first semester material that we learned. And if you recall, the domain is all of the x values and the range is all of the y values. So for this exponential function, What are our x's doing? What are all the possible x's that we could have? Well, x in this exponential function, x can be all real numbers. But it asks us to write this using inequalities. And so to do that, we would say x can go from negative infinity, x is greater than negative infinity, and x is less than positive infinity. Now, why can we not be equal to? Well, you can't be equal to infinity because we can't define infinity. So this is what we would say. The range, let's see, we didn't do the range. The range, y values are going to be greater than 0, but we said we'll never get to 0. We just approach 0. We never actually get to 0. It just looks really, really close. And then y can also approach infinity. So y is going to be less than infinity, but greater than 0 in this case. Now it asks, what is the y-intercept of the graph of the function? Where are we crossing y? And so in order to find that, we can go into our table and see when x is 0, what is y? And right here, when x is 0, y is 200. So the y-intercept is 0, 200. And we'll learn later that that is the, that's a, that's the initial value. Actually, we've already seen that. Next, we have a vocabulary term right here. An asymptote of a graph is a line that the graph approaches more and more closely. Identify an asymptote of this graph. So I'll go back to the graph. We have already talked about, right here in part C, that our graph is going to approach 0. So do we have a line there? Yes, we do. We have the line y equals 0, and that is the horizontal x-axis. That is the line that this graph will continuously approach but never quite touch. So that line, y equals 0, is the asymptote of this graph. It's also the x-axis. You're going to see the asymptote y equals 0 repeated a lot. It occurs in a lot of exponential functions. So when in doubt, assume the asymptote is the x-axis, y equals 0. Next, why is the value of the function always greater than 0? Well, when you're multiplying by numbers that are not 0, you're never going to get a product of 0. So that's why we can get really, really close to 0, but never actually end up with 0. Multiplying by numbers that are not 0 will never have a product of 0. All right, go ahead and let's turn on to page 618. And then we'll talk about the end behavior for decay functions. Now decay, as you probably predicted or can tell by the wording, by the vocabulary, decay is going to mean it's going to be a graph that goes down in some way. It might go down like this or it might go down like this, but we're going down. All right, so use the form from the first exercise to graph another function. So here again, they give us the function that they want us to put in the calculator. And we'll talk in just a few minutes about the difference between the first one we graphed and the second one we graphed. That difference really lies right here. In this case, with a decay function, we have a decimal value in the parentheses. And in our original one that we did with the growth, we had a value of greater than 1. So keep that in mind. Let's go ahead and clear out the one we had, and we'll input this new one, 500. Again, I'm on the y equals screen. 500 times 0.8 to the power of x. And they give us another viewing window. So I'll change my window. And we want -10 to +10 for the x-axis with a scale of 1. -500 to 5,000 with a scale of 500 for the x-axis. And now I can go and take a look at my graph. So here you see the decay taking place. It's getting lower and lower and lower and lower because we are repeatedly dividing in this case or multiplying by a number less than 1, which would be a fraction, When we multiply by a fraction, that's the same as